Ilmas, our men is working together with China. It's a pleasure. And then we have very
your bricks then have to be broken again into a grain size that they need.
Yes, probably.
Yes,
probably.
So please welcome Vladimir to introduce us to ALUSAL. Thank you.
Well, thank you, Mike, for inviting me here, and thank you, all of you, to be ready to listen to my explanations about ALUSAL. Why ALUSAL? We have Hydrosoul, we have Biosol, we have Cryosol, and we have also ALUSAL. ALUSAL is a process. We give these processes names because that makes it easier to communicate and to keep track of what we are doing. ALUSAL is a process to recycle the flux salts. It's not only the sodium chloride, it's also the potassium chloride, and it's really the potassium chloride that makes the process either economic or not. This is the story. It started in June 2007. Mike Gill sent me an email. I thought, well, interesting. I spoke to him, and as we spoke, I thought, well, yes, I think our process could be applicable. Although the Hydrocele process is for removal, for extraction of magnesium salts and other impurities from salt, and the extraction is done with sodium chloride solution, with a saturated sodium chloride solution. Here, with this ALUSAL process, we want to extract salts from slag, from the Dross. So it's an entirely different chemistry, but the principles are really the same. So we have done some tests. 2008, the contract was signed in June 2008, and the engineering package we have supplied about 4 months later, and in 10 months the plant was actually built. This is a rotary oven. What we can see here is the molten aluminium that is being poured out. In the rotary oven, the rest, so the waste of aluminium is being fed, is being molten, heated up, and to avoid the oxidation of the aluminium, it is covered with a mixture of sodium chloride and potassium chloride, plus some about 3% of the cryolite of the fluoride. And after the aluminium is poured out, this shows how the aluminium is being poured into the forms to form the ingots. After the aluminium is poured out, as much of it as possible, the hot aluminium oxides, or the dross, is being removed. And as you can see here, there is still some aluminium in the dross. So what is then being done with it is that the dross is thrown into a cooler. It is then crushed and it is screened. The larger pieces of aluminium are removed and recycled, and then the dross is left. Now the dross is a slag. It consists of about half of the salts and half of some aluminium oxides and other ashes remainder of the beer and Coca-Cola that still was in the cans. Now, the very unpleasant thing about this dross is that when it gets wet, it begins to smell terribly. Not only ammonia, but it's all kinds of other very, very unpleasant smells. So to dispose of it is difficult. It has to be disposed of dry, and it's an expensive story. On the other hand, the half of it consists of the salts, and the salts again, half of it is the potassium chloride. Around 2007, 6, 7, 8, when this project was conceived, the cost of potassium chloride was on average $700, and the peaks reached up to $1,000 per ton. Salt, sodium chloride, was delivered dry, perhaps at 50. So it's not the sodium chloride, it's the potassium chloride that is important. This is another view of the site of the factory where we have said, okay, we can put the plant here. And we have signed the contract. Then this is a description of what this ALUSAL actually consists of. First of all, the dross has to be crushed, milled, screened, and the metal aluminium has to be separated. For each one of these unit operations, you can either use something rough, as it was done here, or something more sophisticated. For example, the crushing and the milling can be done in phases, and then you are producing much less of the very fine dust that is unpleasant. Also, the metal aluminium can be done just by screening, or even by some eddy current separators. The Hydrocele process is the key of this process. The problem with washing or leaching of salts from some solids is that you can't do it up to the final point. You mix the dross with water, the salt dissolves, but there is still some salt left, so you separate it. Then you have to re-wash it. You are again producing diluted solution of the salt, and because it is still, the dross is still in a salt solution, there is still salt in the dross. So we said, okay, our countercurrent continuous process would be or should be capable of, on the one hand, producing a really salt-free slag, and on the other hand, producing a near saturated sodium chloride solution. The solution then goes to an evaporator and crystallizer, and there, if the solution is diluted, you have to first evaporate water before the crystallization starts, and that makes the whole process much more expensive. It's the main energy, the steam or electricity consumption that is taking place here. So, on the one hand, slag without salt, on the other hand, near saturated solution for crystallization. And then, of course, we have the slag that needs to be dried, and packed and delivered, sold, marketed, and also the flux salt has to be dried and made ready for use in the ovens. The Hydrosol is a countercurrent process that can do this job, and this is what we have done here and what was actually successful. Now, let me explain how this process works. Now, conventional process is that you mix water with some solids, you dissolve what is soluble, and then you separate it. You separate it, for example, in a centrifuge, but you can also use a filter for that. You get, on the one hand, the feed, that's here as the salt, shown as the salt here. Then you put the water and you get the purified salt, or here in this case the purified salt-free slag. Now the principle of the Hydrosoul process is that you actually do not put the water in the centrifuge or on the filter. You put it into a filtrate vessel where you dilute this filtrate, and any solid particles that are present in this filtrate are then dissolved, and this pure solution of the salt is then used for the hydro extraction. In this case, in the ALUSAL process, it would not be the salt that is dissolved in the filtrate vessel, it is the pure water that comes at the end of the leaching process out and is being recharged to the hydro extractor for the leaching. The leaching actually takes place only in this lower part of the hydro extractor here. Here. That's where the countercurrent flow of the solids against the flow of liquid or of the solution upwards takes place. Then, of course, we have to get the stuff somehow to the hydro extractor. This is what we do with hydraulic transport. We mix the salt with the overflowing brine and pump it to the top of the hydro extractor. And then to close the loop, the overflow from the elutriator flows to a settling pond from where we then pump the brine back to the hydro extractor and to the elutriator to adjust the countercurrent flow the way that we need it, that we require it. This shows some development of the countercurrent. The countercurrent is not easy. It's actually rather difficult to do it, because if the conditions are not correct, then the countercurrent flow goes by channels, and there is a channeling of impurities with the solids in the downflow, and a bypass through channels of the upflow. What you see here white is salt, solid salt crystals flowing down, and the black spots is brine that is colored with black ink to make it visible. So what you can see here is that, first of all the black brine flows upwards, that is here and here. Below the injection point of this black brine, you do not see any black brine at all. It is all moved upwards. And then you can see that there is some diffusion of this black brine in the upper section, that's here, here. So that you need a certain height, a certain elevation. It's like distillation. In a distillation with packed column, you have the theoretical trace, and you need a certain number of these theoretical trace to get really the heavy liquid down and the light liquid up. So this is these are the chemical engineering principles of the process. The most important one. There are others that I am not going to discuss. Now, this is the completed plant. It consists of the cooling and the crushing that you have seen in the previous picture. That is here. Then you see you don't see the elutrate, but you see the hydro extractor. This one. It's pretty high. For the reasons that I explained before. You can see the filter. You can see the brine tanks. You can see the cooler and the steam generator. and the evaporator crystallizer. Right, this is the Heydrich Structure. You have seen this picture on the handouts that I have distributed to give you something to bring home. This is how we have been examining actually what is inside, where are the solids and where is the liquid. You don't see anything, it's all just black and grey. It's a very, very messy thing. This is the filter, that's for the filtration of the desalted slag. The brine tanks, the Heydrich Structure. You can see the particular funny shape. This shape is necessary to actually break the channels and to make the Heydrich Structure working. And in the background you can see the evaporator crystallizer with a rather oversized solid discharge of the solid, of the crystallized solids. It's here, this one. That's where the crystals are drawn out, the evaporator body, the vapor line, and the condenser. Condensate is then fed to the steam generator, and steam is produced to heat the evaporation process. This is the outlet of the crystallized salt, sodium chloride and potassium chloride, on a vibrating screen. It was a very good decision, instead of using centrifuges here, just to use this vibrating screen doing a partial dewatering, because actually the residual water evaporates immediately in the rotary oven. This is Mike Gill, the general manager, cleaning the distributor. Rough guys, very, very, very rough guys. I think most of our environment, safety and security and health officers would, well, I think they would just, the hair would stand up but it was done very quickly, there was no accident, and well, because the boss did the most difficult part of the work. And this fellow, Dale Haberny, he was a genius. We supplied the basic engineering package. He gave me a call, asked a question. In the basic package, you have a sketch of the Heydrich Structure, and it shows 4 distributors, but in the specification you only have 3, which is correct. I said, well, the sketch is general, the specification is specific, so it's 3. So he put in 3, and that was all. I asked him, when do we get the drawing for checking? Oh, we will make the drawings perhaps afterwards. And a few months later I was called for the startup of the plant. So he built the plant without drawings, just on the basis of our sketches, of our specifications. Genius. That's the 5 of us in the middle. Mike Gill, I'm on his left, here on the picture on the right, Dave Haberny, Vlad Vaniek, my representative in America, and the president of the company, who was the main salesman. Acceptance certificate. So, if you have a problem with salt, why don't you turn your salt into gold? Gentlemen, ladies, thank you very much for your kind attention.
So you mentioned some magnesium salt extraction. Is that possible?
Well, yes.
What are the results of that?
Right. Most of the plants that we have built were built for purification of sea salt, solar sea salt. And solar sea salt crystallizes from the so-called pitons, which consist of magnesium chloride and magnesium sulfate. And the other portion of the salt is still the sodium chloride. Now, pure salt, whether it's for the caustic chlorine production or whether it's for human consumption, must not have the magnesium. So the magnesium salts are being removed by the Hydrocele process from this salt by Heydrich Structure. The salt is not clean, clear and homogeneous crystal. It has crevices and cavities, just like most of the slags have. And the removal of these more soluble salts from the salt, and in this case, in the ALUSAL case, the removal of soluble salts from the slag takes time because it goes by diffusion. It has to come out from the crevices by diffusion. So it needs time, and that needs an equipment of the appropriate size.
And has anyone been developing that on a commercial basis?
Yes.
Use being made of the magnesium salts?
Yes, normally in solid salt works, and it's really quite a big industry. It's about 1/3 of the total salt produced in the world is produced by solar evaporation. That means it's 100 million tons of salt per annum. And these bitterns are removed, and they are normally sent back to the sea. Of course, they contained this magnesium chloride, magnesium sulfate, and theoretically it would be an excellent raw material for example, precipitation of magnesium hydroxide, and then by dewatering the magnesium hydroxide, magnesium oxide of very high purity can be produced and then used for special refractories.
Thank you very much. That's very interesting. Any other questions for Vladimir? Okay, if not, I'm sure he'll be around for a bit. He's got his exhibition table outside as well. So thank you very much again. Thank you, Vladimir.
Netherlands, but no, I don't know. Look, Mike, I give you this press release. This is the latest that we do. It's 3 million tons of salt per annum. We just got the job.